Hello. Today I'm going to present the paper which is Imagenet classification with deep convolutional neural networks. This is called as AlexNet, which is very famous paper which tried to use deep learning architecture first in the Imagenet challenge. And before starting my presentation, I wanted to talk briefly about my channel because this is my first time to post a video, actually the first public video in my channel. So to be short, I'm going to post videos about papers I'm interested in or some lectures about my interest fields as well. And the reason why I started this is to study papers, as it can be a good chance for me to review papers I have read or will read in the future. Okay, so let's begin my presentation with the paper called Imagenet classification with convolutional neural networks. And let's first see the overall architecture first. Okay, this is the figure, and as it can be seen in the figure, the AlexNet is a kind of convolutional neural network architecture for image classification. That is, from the input image, like this can be seen as image size with 224 by 224, and there are 3 channels in the image, which is the RGB each. And this image is going to be the input of the overall architecture of AlexNet. And the output is 1000 categories, which represent 1000 image classification, like dog or cat or other things, and so on. Total 1000 classes. And the 3D boxes over the left side here is the convolutional neural network architecture for extracting the features of the image. And the last 2 dense layers, which is fully connected layers, is going to be the take role of classifying the image from the given embedded features. And as you can see in this figure, there are 2 parallel streams of the network, but this is used because at the time there was limited GPU resources, so they used the 2-stream architecture. So this is rarely used these days, but it can be also still can be used in very big architecture or if there are many parameters to train. Okay, so this is the overall architecture, and I'm going to focus on each factors that this paper uses for the training. So I'm going to explain each section by section to explain this. So first, the dataset. As I said that this is just an image classification architecture, the dataset is a collection of images. There are many images, and there are 1000 categories. So it's just a collection of images. And ReLU non-linearity. Before ReLU came out to the world, the activation functions were usually tangent hyperbolic function or sigmoid function. And the author of this paper, as far as I know, first made use of the ReLU activation function to prevent the overfitting issues. And to elaborate a little more about this, this is kinds of activation functions that are used previously or these days, of course. And these 2 functions, sigmoid and tangent hyperbolic, was the mostly used activation functions before ReLU came out to the world. And the problem of sigmoid and tangent hyperbolic was that the gradient become closer to the 0 at each side. So with bigger and deeper networks, because the gradient should be backpropagated through the whole network, the gradient of 0 are stacked through the backpropagation, and the total gradient becomes 0, almost 0, so the network stopped at some point. So this was the problem of the gradient saturation problem. So this paper suggested to use the ReLU function, which is the abbreviation of rectified linear unit, because there are two linear units combined together. And this has the advantage of there are no gradient saturation problem, because the gradient always 0 when the input is lower than less than 0, and the gradient always 1 when the input is more than 0. So this is the reason they use the ReLU non-linearity, which is ReLU activation function. And the next thing is that they used multiple GPUs, and as I already said in the overall architecture here, they split two main streams to divide the architecture, and each architecture goes through the different GPU, because there was GPU limitation that days. But these days, there are many team running specific GPUs these days, so it's not a big deal in these days. But of course, it can be still used to train the big models, which requires much time, or many parameters to train. And the next one is local response normalization. It's just kind of normalization on the patches in the images, local patches. And as you can see in the equation just describes that the summation of local patches, scalar values of the summation of local patches is going to be the denominator, and numerator is going to be the center pixel value. So it's just kind of normalizing the value based on the local patches. And the author said that this helps to increase the accuracy of the model, but it is not used anymore, because the later researchers found out that this normalization does not really help for the performance. So I'm going to just briefly mention about this one and going to next one. The next one is overlapping pooling. As you may already know about the pooling layers, pooling is kind of operation to reduce the receptive field. Reduce the size of the activation maps to reduce the parameters efficiently, because there are no non-number parameters when doing pooling. Of course, there are various kinds of pooling, but the max pooling, which is still maximally used these days, doesn't require any non-number parameters, so it's really efficient. And the author of this paper used overlapping pooling concept, which is, as it can be seen in this figure, the pooling operations are done with overlapped reason, and by doing so they can mostly make use of the overlapped pixel values to reduce the overfitting issues. This is because they use overlapping pixel values over and over, so that the pixel value is not used once. By using multiple times, it can have kind of aggregating many pixels to make the result. So this is kind of the reason they use overlapping pooling, but as I said earlier, the purpose of pooling is kind of reducing the activation map efficiently without any learnable parameters for faster training time or faster inference time. But the overlapping pooling, since it has lower stride compared to non-overlapping pooling, the result of its activation map is kind of bigger than the upper side. So this one, the overlapping pooling is not rarely used anymore. It's not used anymore as far as I understand, as far as I know. So I already mentioned the overall architecture previously, and as I said, the image is the input of the overall architecture and goes through the CNN and convolutional neural network and fully connected layers to generate the output of 1000 categories. And the section 4 is about reducing overfitting. So they utilize several techniques to reduce the overfitting issues, and I'm going to introduce one by one. So the first one is data augmentation. Data augmentation is already a famous technique that almost everyone in computer vision fields already knows. It's kind of augment, manually change the data slightly to make the dataset fluently. The data is bigger with more features. So they used random crop, random flip, and so on. These kind of techniques are called data augmentation, and they utilize the basic augmentation techniques here. And the second one is utilizing the PCA to subtract the main data distribution axis value, the kind of mean value, to obtain the more representative features before put the input to the network. So these are not used anymore also, but this is kind of similar to the technique which is normalization of the input image. And these days most people uses just mean subtraction and divided by standard deviation. And PCA, of course, PCA is more sophisticated skills to normalize the image, but even utilizing not normalized images into the input image gives the relatively reasonable performance, so this is not used anymore. And the dropout is kind of techniques to deactivate such several neurones when training for each iteration, each epoch, or each iteration. So this is kind of making new architecture each iterations, because several neurons are deactivated and only the survived neurons are connected to generate the architecture. So it is called that this kind of dropout techniques is similar to the ensemble effect, because the various architectures from each iterations are combined combined to give the final output, kind of ensemble of different architectures. So for the details of learnings, they used stochastic gradient descent, which is a very famous technique, and electrification was utilized. initialization, and also running rate decay for after some iteration, after some epoch. So this is just the running process of neural architecture, and the next section. For the result, they surpasses the previous best performing architecture, which utilized the shift and I don't know if it is, but it's kind of classifier, I guess. But I was really amazed that just using CNN, which is trained by the computer, over surfaces the shift, which was very famous feature extractors before the CNN came out to the world. I was really shocked because shift has many mathematical bases, mathematical features, and really hard to understand at the first, but CNN is kind of really easy compared to previous Bayesian algorithms. So they achieved the state-of-art performances. For the qualitative evaluations, as you can see in the figure, the classification performance is quite good. And as you can see in this figure, each rows have similar features after CNN feature extraction. Yes, I guess. So it shows that this kind of CNN-based deep neural architecture shows the good performance. And the next discussion. Yeah, I wanted to mention it before, but it's kind of discussion will drop out because some of the neurons are deactivated. The remained neurons consist the different architecture compared to the architecture where the neurons are all connected. So this kind of new architectures are combined to generate the output, so that it has the effect of ensemble method. And for the last slide, this is the filters on the first layers of the CNN architecture, the AlexNet, and it shows from the upper side, the filters are used to extract the edges or blobs as it can be seen in this figure. And the amazing thing is that this kind of filters were 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 tried to made by researchers manually before the deep learning came out. The CNN came out. I mean these filters are similar to the filters made by Bayesian researchers before CNN came out to the world. So it means that the CNN architecture can generate the filters that the human could do, and it implies that it can be do better than the human knowledge. And for the bottom side, it shows the color filters. For example, the green ones are usually utilized to detect glass or trees or something, or this kind of that area is going to be the extraction of the kind of texture. So this is the end of my presentation, and thanks for listening. Because this is my first time to first record a video, the quality of video is not that good, I guess, but it's yeah, not that good, but if there is someone who wants to understand more deeply, I can answer your questions on the comments or email or something. Okay, thanks for listening for my presentation, and thanks.